Hello guys, welcome to my fourth tweet. Today I would like to talk about the most important study items of the fourth step of machine learning course at CS internship. While passing this step, I had a long journey. After learning all of the study items and doing each specific task, I was wondering if I could maneuver on the most important and practical study item of this step with the topic of the role of probability and statistics in machine learning. If you've been following CS internship tweets, you would have known that when coming through the ML tasks, we use Mathematics for ML book by Mark Peter Dizenroth, et. While reading the statistics and probability chapter of this book, I was so impressed by the diagrams and shapes of this chapter. While reading the chapter, I realized that some of the stuff need more explanation than they do in the book. Thus, I decided to bring them here to explain more completely. Let's get started by the first tip. So, the first part of this chapter had introduced the most basic definitions such as sample space, event space, and the probability space. By the sample space, we mean having a set of all possible outcomes, which is usually denoted by this symbol. You can see it here. And when mentioning only a subset of it, we are using the event space, which is usually denoted by the A alphabet. And finally, if you want to measure the probability in which that specific event will occur, you are using the probability space described by P of A. Now, the second part was focused on the types of distributions which are discrete and continuous forms. As you could guess by each of their names, a discrete distribution consists of the data which we could gain from certain values. The continuous distribution, in contrast, focuses on obtaining any value within a particular range. But the point is how we could implement these distributions on the random variables. It is actually the hottest part of machine learning, which consists of the maximum fans. Here we could gradually work with the discrete and continuous distributions in each diagram we want. Now let's get more familiar with the usage of these distributions on the next slides. The values gathered from these distributions will gradually form an important distribution which is called correlation. The key point is the way they gather together. Let me show you this slide to see what I mean. Well, correlation aims to a super important distribution which is called Gaussian distribution. Let's go through the next slides to get more familiar with the Gaussian distribution and its role in machine learning. Well, the simple type of Gaussian distribution is called univariate distribution. As you can see, it is bell-shaped. I've brought its formula for a further reason, not just memorizing it. Let's check another type of Gaussian formula, which is a lot more complex than the previous one. From now on, I would like to focus on this kind of distribution, which is called multivariate distribution. Okay, now take a deep breath and describe what extra stuff you see in its formula that haven't seen before. Look at the univariate formula and the multivariate formula. Yeah, eureka, we made it. As you can see, there is an extra sigma in the multivariate formula too. Although having the mean and variance, it has another thing which is called the matrix, covariance matrix. This is exactly the point which makes a multivariate Gaussian distribution. Okay, now imagine you have two specific values for the mean and these values for, you can see them, these values for the covariance matrix. I want you to pay as much attention as you can to the covariance matrix. See what happened? Now look at the new values of the covariance matrix. There becomes a new diagram. Look at the next ones. I've brought you some more examples in which the mean is the same. However, the covariance matrix differs each time. You can see them. Alright, in contrast, imagine keeping the covariance matrix the same, but varying the mean values this time. Please focus on the mean values which I want to show you. Look at here. We've got the values 5 and 4 for the actually mean value, and the covariance matrix, which is denoted by a sigma, which has these kinds of values. See what happened? There becomes a new diagram. Now, look at another example in which actually we have kept the covariance matrix the same, and actually we've got the probability class of 1. See what I mean? As you can see, although the shape of the matrix is actually has changed, but the spread of the matrix has changed too. Look at another example. I've got the actually probability class of 0. See the previous one? The probability class was 1, but the covariance matrix is the same. In this example, the covariance matrix is the same too, but as you can see, the actually probability class becomes to 0. You can see the spread and position has changed. Now, let me go to the previous example. As you can see, when having the mean, the mean values the same, but different kinds of covariance matrices, we would have the spread and position in a particular way. But as you can see here, the mean values are the same too, but the covariance matrix has changed. Although the position has a little bit changed, but the spread and shape of the diagram has not changed. Look at this example. Again, we've got the actually particular values of the mean values, but the actually a different kind of covariance matrix with some different values. See what I mean? Again, the spread and positions are the same, but as you can see, the actually the shape of the diagram has changed a little bit. Now, let me go further. In this example, as you could see, I've changed the actual probability class to 1, but I've kept the covariance matrix the same. And example, the mean is 5 and 4, but the covariance matrix is the same. Look at the shape of these diagrams. This example is way more different than this example. So, what we understand from these examples is that if we keep changing the values of the covariance matrix, actually we are working on the position of the specific distribution. However, while keeping the covariance matrix the same and changing the values of the mean each time, we are changing the spread and the shape of the distribution. As you could see in these examples, we had a particular shape of the diagram. As you could see, actually the spread and the shape of these diagrams have not been changed. But in another examples, see this one is higher. This one is a lot lower, and as you can see, the spread has changed a lot. So, the most important part of my tweet is that if you could actually know what you're doing with these formulas, that for example, I want to change the mean values this time, or for example, next time I want to change the covariance matrix values. Actually, memorizing these values may not help you all the time. We should know that actually what we are doing with these formulas. Please, please, please gather each shapes and actually know what you're doing with with these diagrams. Because only memorizing the formulas, I don't think that will help you a lot. Alright, and this is how a multivariate distribution is made up of the univariate actually distribution. As you could see, with more than two or more than two univariate distributions, we can gather a multivariate distribution. I've already brought you the shape of a multivariate distribution. Look, if we've got actually only the variance and the mean in the formula that I had shown you before, like this, then we would have only a univariate actually Gaussian distribution, which is like this. This is so simple, and I have shown the mean, sample, and the actually sigma of this formula. But as you can see, these two formulas, I mean the multivariate formula and the univariate formulas, are a lot actually really the same. Only as you could actually figure out the sigma point, which I also referred to it as a covariance matrix, has made up a new distribution, which is called multivariate actually distribution. But please pay attention that not only two univariate distributions we've got for making the multivariate distribution, we've got two or more than two distributions for forming a multivariate distribution. This is really important in actually a topic which we call evaluation in machine learning. It's one of the hottest topics that we use, and implementing it refers to big projects such as molecular biology, I don't know, cryptocurrency, cryptography, etc. Let me keep summarizing what we understood, that the basic definitions were referring to a really important distribution which was called correlation. By correlation, we understood that we can have multiple kinds of distributions, that one of the most important subset of them was the Gaussian distribution. And also we understood that Gaussian distribution consists of two actually important types. That the first one is univariate and the second one is the multivariate distribution. The univariate is like a bell-shaped form. However, the multivariate is gathered from two or more actually univariates. And by gathering the perfect correlation, we will understand that we can have a multivariate distribution not only for sample actually spaces and not very complex distributions, but for implementing more complex codes. And I also reviewed that actually these multivariate distributions are so practical in the machine learning world. You can have further information. I'm on LinkedIn that I will have my account on this Twitch, that you can follow me for more information about these types of distributions. All right, guys, thank you so much. I really wanted to actually maneuver on the mathematics study items in this tweet. I didn't want to go deep on the codes. I will go on them for the next step. Thank you so much. And if you liked my video, please subscribe to my YouTube channel. And please don't forget to like this video on CS Internship channel. See you all at the end of the next step. Thank you.